Now we can talk about centroids of lines. Say our body is a wire, and our wire has a uniform cross-sectional area denoted as A and a length L. The mass of our wire is simply equal to our density times our area times our length. Recalling area times length is going to give us volume. Thus, in differential form, we can express dm as rho A dl. Thus, we can express the centroid of a line by looking at our center of mass expression. That is, x bar would be equal to the integral of x dm per the integral of dm. If we make the substitution for rho A dl for dm, we'd have the integral of x rho A dl per the integral of rho A dl. Rho and A are constants, which get removed from our integrand, and we are left with the integral of x dl per the integral of dl, where dl represents the differential length of our wire. It follows y bar is equal to 1 per L, the integral of y dl, and z bar is equal to 1 per L, the integral of z dl. To see this in application, let's determine the centroid, i.e. x bar and y bar, of the wire shown below. We have a wire with a radius r that goes from 0 to 90 degrees. To begin, we'll look at x bar, and to do such, we will need to determine a differential length. Our differential length is drawn on the image below. The differential length is just a segment of our arc length. That is, dl would be equal to r, our radius, times d theta. D theta is a small swath of an angle that we will trace out. X in this situation is simply r cosine theta. Thus, x bar is equal to the integral with respect to L of x dl per the integral of dl. Now, once we make these substitutions, we have the integral from 0 to pi over 2 times r cosine theta, r d theta. And this is per the integral going from 0 to pi per 2 of r d theta. R is constant, we'll remove that from our integrand. Thus we have r squared times the integral from 0 to pi over 2 of cosine theta d theta per r times the integral going from 0 to pi over 2 of d theta. Now our denominator is quite easy. We have r times theta, where theta is evaluated between 0 and pi over 2. Within our numerator, we have r squared times sine theta, evaluated between 0 and pi over 2. Thus, we are left with r squared per r pi per 2, which gives us 2r per pi. Likewise, for us to determine y bar, we are going to have the same expression for our differential length, which is r d theta. Thus, y bar is equal to the integral of y dl per the integral of dl. When we substitute in these terms, we have the integral going from 0 to pi per 2 of r sine theta, r d theta, per the integral of 0 to pi per 2 of r d theta. R is constant, we will remove that from our integrand, and we are left with r squared times the integral of 0 to pi per 2 of sine theta d theta, per r times the integral of 0 to pi per 2 of d theta. Once again, our denominator is quite easy. We have r times theta, where theta is evaluated between 0 to pi per 2. And we remember, the integral of sine gives us negative cosine. Thus, we are left with r squared cosine theta, evaluated between 0 to pi per 2. And we'll bring that negative sign out front of this term. Evaluating this, we have r squared per r times pi per 2, which gives us 2r per pi. If we look at these centroidal values in comparison to the radius that defines our wire, we are actually going to be off our body. And that's okay for lines. Oftentimes, the centroid of a shape that is constructed by a wire is not going to exist on the wire itself.